Good afternoon. This is CIVE 638, Sedimentation Engineering. And this class is 082, meaning is the 8th week, the second class. Today is Thursday, October 13th, 2022. I'm Professor Victor Ponce from San Diego State University, Department of Civil Engineering. And the subject today is still morphology, fluvial morphology, river morphology. We have discussed the Lane equation, and by now we are already through with it. So I'm going to now go into a couple of, should I say, sophisticated? Actually, we're going to discuss the other project or endeavor that Lane got into. What I'm going to say today is an interesting story. And I'm going to also make a confession to you. Can I do a confession? Yes, I can. Emory W. Lane wrote that famous paper, 1955, which everybody talks about. He's a famous guy. But hardly anybody knows that he also wrote another paper in 1959. But for whatever reason, it wasn't really published. Now, I think I already told you that Emory W. Lane was a professor at Colorado State University. And in 1959, he got together with a couple of students from, I believe, from Chinese extraction, judging by their names. I think one of them is Liu and the other one is Li. And they wrote this paper. And I can't tell you exactly, I don't know, and neither I wish to know, what percentage of this work is Lane's and what is from the students. Typically, the students are the ones that do the work, and anyway, it works together. I've done a lot of papers, both for professors of mine, as well as for students of mine working together, so I know what I'm talking. But this is an interesting paper. And why is it interesting? Because it is extremely difficult math. It's algebra, it's calculus, it's mechanics, and it's extremely difficult. And this morning I was reviewing it as I always do, and I'm telling you, I'm going to confess to you that I didn't get through even 20%. It was going to take too long for me to do it. So I'm giving it to you as is. So there's two ways to look at this thing. One is I'm going to find out what he did and learn from it, okay? And the other one is, well, we already know what he did and we know the answers and the results, and we can use the results. We can trust him in terms of how correct it was. Now, this finding or this paper is not very well known. I have to dig in deeply to get it. I got it in the year 1982, I believe. Right, it was in 82, exactly in 82. That I was doing some research on channel morphology for the National Science Foundation. And I had to dig through all the literature of the time, and I found out this paper. So I promptly secured the paper and read it, and I was, of course, oh my gosh, how are we gonna get through this? And you'll see it in a minute. And then eventually, since the paper was obscure, because it had been written as a report, a Colorado State University report, and I know if you wanted to get the original, you could make an effort and go to the interlibrary loan and get it for sure. That's a good system. I haven't used it in 5 or 10 years, but it used to be anyway a good system. Libraries around the world have connections, and they can get you the report if they don't have it. And I'm 100% sure that that report was not in existence on the shelves at San Diego State, but it was at Colorado State. And I got the book, I got the report, I read it. And I believe at the time we had the money to employ students. And I had one of our students scan it and type it. Yeah, I believe so. I don't remember at this point. It's been exactly 40 years, right? But the point is we had this produced, and we had a hard copy, and it was all fine and dandy. And then 2-3 years ago, I had a student from China that came over here and worked with me for a couple of years. And then at the end of her tenure, I charge her with doing this work that we're currently looking at. And what is this? This is just a paper by Lane and Liu and Lin, but in HTML form. In order for us to do that, she had to, of course, run the procedure that we always do, which is scan the JPEG. It used to be JPEG, now it's PNG. Scan the image, put it into digital form, and then clean it up. But the thing about it is that this mathematics is so complex that the cleaning up of the OCR, by the way, in case you're not familiar with the term, it means optical character recognition. So a machine that will scan it and will recognize it. But the more difficult the algebra, the more difficulty it has the machine in recognizing the straight English, which is not straight English, it's straight calculus. So it becomes a very difficult job to clean the OCR. And Shuroi, her name was Shuroi. Shuroi Jian did a great job. And here it is, okay? Here it is. Look at the math. Look at the math. How many equations? Look at the math. It's amazing. There's about, I don't know, 50 equations, and they're all trigonometry. It's basic trigonometry and calculus too. There's integrals in there and so forth. It's a very complex thing. It's among the most difficult things, or transcriptions, because I didn't do this. I transcribed it and cleaned it up for clarity from what Lane had said, trying to keep in mind that I was not going to change anything. And it was difficult job at the beginning in 1982 when I did it with another student. And then it was difficult in the year 2019 when I did it with Shirei. And here it is. We published it in the year 20th. That was already during the pandemic, right? The pandemic was 20. During the pandemic, Shirei was still working with me and we were doing this work. So this is what the thing is all about. Now, I'm going to go over, briefly get started here, and then I'll jump towards the end and I'll tell you another story in relation to this project. As a matter of fact, this morning it occurred to me that maybe, just maybe, we didn't do 100% of a good job and there's maybe a bug in there. And I don't like bugs, but I understand there's always bugs creeping up in anybody's work. So I am charging one of our workers, one of our students now, to, I have associates, different associates who do different things for me. And he happens to know his math really well. So I'm charging him that in the next month or so, he's going to go over this paper with a fine-tooth comb and find out if there is any errors, typos or otherwise. I honestly don't think there's the otherwise, because I went through it. I went through the math and verified everything he had said and agreed with him. So what we could have in here is a typo, a plus and a minus, and so, well, that could happen. So I'm going to try to fix that in the foreseeable future, in the next couple of months or so. But you won't see it because you're not going to have the wherewithal to run through this and find a mistake. I honestly don't think so. I'm not asking you to do that. Okay, so what did Lane do? The Lane theory, 1959. So this is not 1955. For the equilibrium shape of self-formed channels in non-cohesive alluvium has been revisited with all assumptions and derivations clearly stated. We did that. We have a knack for clarity. So we can take a paper, a difficult paper, and put it in simple terms that most people can understand. The results are used to estimate self-formed top width maximum depth ratios. It's a function of self-formed top width maximum depth. Rivers are going to self-form their channels no matter what, one way or the other. So we're talking correctly here, self-form. Top width maximum depth ratio. So we're talking about a shape function in here. The ratio between the top width and the depth is not a complete shape function, but it is like a parabola as shown in the figure. So this advances the issue of fluvial geomorphology, because this equation is the only equation of its nature existing in the field. He was the only one that did this work, 1959, okay? So I was interested in 1982 because we were trying to develop a model, and we certainly had no way of figuring out the width. So I figured if I could get a width function, which I didn't think it existed by the time, we would be in good shape Fortunately, I found Lane's paper, and I'm presenting it to you today. I should tell you at this point that as far as the width function, a lot of people have attempted to do it, and they have either not completed or have failed. The only gentleman that came up in the late 70s with a width function, meaning how to calculate the width of a channel, the morphology, right, was Professor Chan, who used to teach us at San Diego State and retired in the year, I believe, 2007, right? And it was Professor Howard Chang that used to teach this class for 30 years. I would say from 67 to 70 to 2007. How many years is that? 40 years? Yeah, right, 40 years. Usually faculty at San Diego State last 40 years, like I have. So he taught that class for 40 years, and then he retired. And then lo and behold, somebody came along, but he or she didn't last. So then I was given the job to taking this class. I took it since 2012. So I've been teaching this class every couple of years for 12, 14, 16, 18, 20, 22. So this is the sixth time I teach this class. But Professor Chang had a width function, how to calculate the width, but he wouldn't tell anybody because he had a model, which he called Alluvial 11, that purported to calculate the width. And since he was selling the model, he could not tell people how he did it, right? And then I don't blame him. People do different things. Different people do different things. He held the width invention to himself. He used to call it the minimization of the stream power, or minimum stream power. And of course, in order to explain that, I mean, you can explain it in different ways, but it's not clear exactly how he did it. But one day, he was nailed down in a discussion enclosure of a paper. And I don't know if you guys are familiar with it. The ones in sediment in hydrology are. And he actually, I couldn't believe it when I read it, but he actually came out and said it in the closure. What was his secret on the width function? And he said it once and he never repeated it again. Okay. I don't know how many people read the closure, but I did read the closure because I was interested in the work that he was doing, even though I wasn't teaching sedimentation at the time because he was doing it, right? And so he basically said, in no uncertain terms, a little bit fuzzy, but he did say that the third relation for the width was the minimization of the changes, of the unsteady changes, so that nature, or rather the process, would try to get back to stability or equilibrium. And he called it very pompously the minimization of the stream power, whatever it was. But so I'm telling you this long story because that was the way he did it. I am assuming that the process, the morphological process, is going to come back, is going to try to come back to equilibrium. Okay, that's what he did. Now, what did Lane do in this paper? He said, I'm going to do this. I'm going to do the shape width function, with depth shape function. And the results are used to estimate the self-formed top width to maximum depth ratio. It's a function of what? It's a function of the friction angle of the non-cohesive material forming the bed. So he was doing non-cohesive material, which is cool. That's the way you start. If you start to put in the cohesion, you'll never end, to be honest with you, because it involves chemistry. And we engineers are not very adept with handling chemistry. That's a long story that deserves more time, but not at this time. But so he said, well, I'm going to use only the physics, only the mechanics. So he says, I'm going to do this function as a function of the friction angle of the non-cohesive material forming the bed. Now, the friction angle is a concept that is very much elaborated in geotech engineering. And I know all of you have taken geotech engineering, hopefully, and know what I'm talking about, the friction angle. The friction angle is the angle of repose of granular material. And it varies between 20 and 45. 45 is for the huge rocks, 30 is for sand, and 20 is for silty sand, okay? Actually, the friction angle could go below 20. It could go to 15 and 10. But the problem is that the lower it becomes, the more cohesion it has, and then you throw in a monkey wrench in there. Exactly how is it that the cohesion is interacting with the friction angle to show the strength and so forth? Obviously, we prefer to treat only the friction angle as clean as it could be, because that is more predictable and can be modeled better. And that's exactly what Emory W. Lane did. He chose to not deal with the cohesion. So this formulation has nothing to do with cohesion. That there is cohesion out there in the real world, of course there is, which means that these formulas that he had derived has to be taken with a grain of salt. Of course, nobody is solving the complete problem. And I stress that, nobody's solving the complete problem. You cannot. You tried your best to do the best you can at the time. I can't stress that hard enough. So that was the friction angle. And then the lift to drag rate force ratio, since it's a co-authorship. They are talking about the force, the lift forces and the drag forces. They came up with the parameter lift to drag force ratio, which simplifies things. It shows the entire formula is only a bit based on the friction angle and the ratio of lift to drag forces. And what's lift to drag forces? Well, I mean, you got to go to the essential or basic mechanics. There's a drag force on everything, and then there's a lift force. The lift force is what allows the planes to fly. And the drag is what allows cars to move. Because if there's no drag, then the cars would slip down and fly all over, and you wouldn't be able to drive. The fact of the matter is a certain amount of friction, which allows you to drive, okay? And the friction is the drag force. So it's all related. Now, the mechanics of this process is very aptly described by Lane, and I am not going to give myself any attribution in here. We regurgitated what Lane had said. The only thing that I did was to try to clear it up from the standpoint of the English language so that it would be more understood by most people that are trying for the first time to read this. And this is something that I have had as a capability for many years, and I continue to have it. I think that a paper could be written at various levels. You could write any paper at a level that most people can understand. You know who does that? The newspaper people. They try to bring it down, everything to 9th grade. And of course, by doing that, they wash most of the meat of it, but they don't really care because they need to get their stuff so that anybody can read it. So they have an instruction. You get it to 9th grade level, otherwise we're going to fire you. If you get too difficult, the people are going to abandon the paper, and then you'll be out of a job. That's exactly the way it happens. So, so that's what we do, and that's what we did in here. We have mechanistic approach. This is a mechanistic approach. Forces, drag, lift, that's mechanics. To determine the shape has been subject to numerous studies. Most notable, oh, there's a bug in here, most notable, that must be a typo, by the way, that of Lane et al. The objective of this paper is to fully document the Lane findings, which, although restricted to the equilibrium case, provide a point of start in the study of unsteady alluvial channel morphology. We wanted to do unsteady alluvial channel morphology, but you got to start little by little. As a matter of fact, towards the end of this class, and hopefully, yeah, we'll get there, I'm going to be talking about unsteady alluvial channel morphology, which is the most difficult thing that I have done. It's kind of difficult because it involves sediment, and sediment is always difficult. Okay. So the assumptions, and I'm not going to go in here in detail on the mechanics. I want to look at the results and the actual methodology. So, but basically there's the main assumptions used by Lane, and we can go over this. It says the side slope of the channel is equal to the angle of repose of the non-cohesive material. I already told you the possible range of angle of repose, typically between 20 and 45. Particles of the range, the 20s are the medium sands, and the 45s are the coarse gravels, big rock boulders, actually. It doesn't seem to go above 45 for whatever reason. I have not seen anything above 45. The particles at the channel boundary are at the condition of incipient motion. The lift and drag forces, together with the downward component of the gravity force, are balanced exactly by the frictional force developed between the particles. The lift and drag forces are assumed to be proportional to the tractive force. The particles are held in place by virtue of this or their submerged weight, resolved in a direction normal to the bed. Exactly. The attractive force acts in the direction of the flow, and it is equal to the weight of the column of water above the area on which the force acts. And the channel is prismatic with negligible secondary currents and absence of backwater effects, obviously. But this is uniform flow, equilibrium, uniform flow. And in this case, it's actually uniform flow. There's a difference between equilibrium and uniform flow. Uniform flow is a prismatic channel. Since this channel is prismatic, it would have to be characterized as uniform flow. If it were not prismatic and you still have steady normal flow, that would be called equilibrium flow. The Lane et al. Method revisited. He starts with a balance of forces that leads equation 1. Then he starts proceeding with the definition of the beta, which is the lift to drag force ratio. He does that because he realizes that he has got the lift force over here and the drag force, and he come up with the beta and he gets rid of both of them. That's a good simplification, because if you can get a hold of the beta, then you don't need either of them, which is fine. The issue at this point, though, is can we find that beta value? And people have done this work in the laboratory and so forth, and so forth. And we at the time had some reasonable values that could be used for the beta parameter of this methodology. So we have at the center line, we have boundary conditions in here at the center line, and we solve for W over delta. Delta is the ratio between the drag force and the local bed shear stress. And delta is just a ratio, a proportionality constant. So the delta went in there, and now we have the quantity is equal, the quantity of the attractive force tas above at the bottom, at the channel center line at the bottom of the channel, is equal to gamma y sub OS, which is gamma YS or gamma RS. And this is gamma YS. It actually should be RS, but in here they're using gamma YS for the simple reason that he cannot mess here with a hydraulic radius. He has to do it with the hydraulic depth. Although the real function in there is a hydraulic radius. So that is kind of a slight limitation. Slight limitation. The wider the channel, the less important is what I just mentioned. The narrower the channel, the more important it would become. So we continue in here, the mathematics, and like I said, I am going to check all this mathematics. I think we already checked it, and Sheree already checked it, and I did check it. But there's so much stuff in here that I don't trust completely anybody's work unless it is done 3 or 4 times, over and over again. So you can see the amount of mathematics in here is actually trigonometry. Trigonometry, I have never done this kind of work as extensive as this, by the way. We've done trigonometry. We have trigonometry in an S-curve, in our S-curve theory, but not as long as and as complex as what you see in here. So then it moves on. And then we have the quadratic equations, the integrals, carrying out the square terms. I'm not going to spend more of your time in here, but then I get to the end. Trigonometric identity, which always helps. And then the sensitivity analysis. Sensitivity analysis formula for the shape of cell-formed channels have been studied by varying the friction angle and the lift ratio beta of lift to drag between realistic ranges. The friction angle for non-cohesive material varies normally in the range 25 to 45. I said earlier it was 20 to 45. This really doesn't matter. It depends on what type of sand you take. But 25 to 45 is what he said. And for illustrative purposes, value of phi were taken from 5 to 45 at intervals of 5, just for illustrative purposes. Values of beta are somewhat more difficult to determine with sufficient accuracy, but we have a reference in here of Apperly, who said that beta reached a maximum of 0.75, decreasing to 0 for 0.90, and then it becomes negative. The mean lift becomes negative. I take that to mean that there's no lift. It's instead the pressure down, because a lift is a pressure up. It's lifting, right? Negative lift means that. Exactly how does that happen? To be honest with you, I can't tell you. I don't know. Why would the lift become negative? But Apperly says it does. And he, to my knowledge, he did it in the laboratory. He was measuring this stuff very carefully. Not too many people have done this kind of work, by the way. I wonder where Apperly's work was done. Let me see that. Apperly's 1968, University of Auckland, New Zealand, in partial fulfillment for the degree of Doctor of Philosophy. Right, that's it. That's Auckland's. Apperly's at Auckland, New Zealand. And we finally figured out the equation that Lane presented, and we vary, just for illustrative purposes, we vary the beta from -1 to +1, but the actual typical value appears to be 0.4, according to the studies of Apperly. So for 45 degrees, we have a width to depth of 3.5. 45 degrees is the highest number. But for 5 degrees, which is already cohesive and not to be trusted at this point, I would stay with 20. So it would be 9. So the variation of the width in normal practice would be between 3.5 and 9, with the 9 being associated with the smaller friction angle, according to the formula that has been derived, which is this formula, by the way. Where is it? It's over here. Formula 57. It's the relationship derived by Lane. The width to depth ratio is a function of the phi angle, which appears here as tangent of phi, which is correct. And the R is defined as beta tan of phi. So it incorporates the ratio of the lift to drag and the tangent of phi, which is obviously the most important parameter. So the R is over here, and as you can see, very simple equation. Actually, this is genius level mathematics, to be honest with you, in order to get there. So we should respect the work that Emory W. Lane. He's a very well-respected gentleman. And by the way, he is my academic grandfather, because he was the professor of Daryl Simons, who was my professor. So it would turn out then that he would be your academic great-grandfather. How about that? Okay, so we got this table that I've already shown. We got this another table. And then we do an online calculation. You know, Professor Ponce can't stay away from the online calculators. We had the simple formula, which is this formula over here. This formula over here that I've already shown you. And we do a calculation, metric. Well, you can't do this. This is a JPEG, but we can do the calculation and get in there. So the concluding remarks is that the theory for the equilibrium shape of self-formed channels in non-cohesive alluvium has been revisited. The non-cohesive alluvium, I would say, starts at about phi 2025. It's a great area in there, because by the time you get to 15, cohesion starts acting. So basically, we would have to say that this theory is not really applicable to values less than 20. But nevertheless, we put it in there to show that what the trend of the computation is. Results are used to estimate top width to maximum depth ratios as a function of the friction angle and the lifted drag force. These findings may be used as a point of starting the study of unsteady alluvial channel morphology. Right, that's what we were doing. We try to get to the unsteady through the steady, because if you don't know the steady, you're not going to get to the unsteady. The unsteady is more difficult. Unsteady work has been my subject for the last 49 years, since I got to Colorado State in the year 1973. I signed up with the doctoral program with Professors Simons and Mahmoud. And the first day I went on to work with Mahmoud, he says, we're going to do modeling, unsteady flow modeling of sediment. I said, cool. And we did it. And we did that work for a year. Actually, I'm going to tell you a story, because Professor Ponce loves the stories. Mahmoud went on vacation the following year. After a year, we had done all this work. And I put together a report of all the work I had done within 1 year. And it's very highly numerical, because what happened was that we were trying to do the mechanics and the physics, but it turned out that we were going to be doing it on the computer. And then the issue of how do you model on the computer numerically. And we learned a whole lot of things with the numerical analysis. It really opened our eyes. And we are good on this subject because of that experience. That first year I was over at Colorado State, we learned a ton. But long story made short, I put this report and I gave it to Mahmoud when he came back. And he, for some reason, I still don't know up to this time, he didn't like the report. Maybe he thought it was too difficult or whatever. So he says, give it back to me. And we sat on the report for a while. And then we later on published a paper that was related to the report said, but it was never the report. So I finally didn't do much with that report. My first report wasn't really taken too seriously, I guess. And it kind of subsided. And eventually I lost it. I lost that first report. I personally thought, since I had put all my energy into that report, that it was a very good report. But I guess not everybody agreed with me. I have one of our associates, his name is Jonathan Wensenberg Mejia Gonzalez. He's an engineer in Peru, in northern Peru. And we work virtually. And I've asked him in the past to show some of the things, because he's highly mathematically oriented. I also was very mathematically oriented, but not now. I can't do that anymore. I don't think I can. At any rate, he did it. He did this work, which is also extremely complicated, by the way. You can see this. When he finally demonstrated that the equation was correct, And he gave me a PDF file and I converted it to HTML. I think I actually did this personally. That I can do. I love HTML. HTML has been my way of life since 1999. So there's 23 years that I've been doing working with HTML. I should tell you, because this is the time to tell a little story. Several years ago, I was in Ecuador at a conference, and I had a meeting with a bunch of professors out there during the lunch. And I was talking about it, or somebody asked me, and I said, well, we don't work with Word, we work with HTML. And one of the ladies that was out there, an engineer, I think she was from geology or geological engineer, she said very pompously, she says, I don't know anybody that works with HTML. That's what she said. Basically, and she said it in front of everybody. That means what she was saying was correct. Otherwise, people would have jumped on her, right? She said, I don't know anybody that works with HTML. Basically, it was telling me that I was out there in a corner by myself, which I was, and I'm glad and I'm proud to be there on a corner by myself. But the point is that I benefit a lot from it, because everything you see on the web is because Professor Ponce doesn't need to hire anybody to put stuff on the web. I do it by myself, and I do it on a daily basis. I've been doing it for 23 years, so I know how to do it. And in the process of that, we had to run into a few experiences which are not very good and great, but that's okay. I'm going to leave that for some other time. Here we have the authors, myself, Shiroi Jiang, who did most of the work of transcribing the JPEG, the image, into HTML. That's because she wanted to learn HTML. Actually, I told her, Shiroi, you should learn HTML. And she says, yeah, fine, professor, whatever you say. And I said, well, I'm going to give you something you can learn. And that's the way to learn, to do it. And this is Jonathan Mejia, who put this demonstration of the limit using L'Hopital's rule, I believe, right? Applying L'Hopital's rule in there. So that's the story about the paper by Lane and the calculation, which I have already shown. So I don't know, well, actually, the calculation is over here. So in here, we could say metric system, the flow depth, say 1 meter, the friction angle, say 30, and the ratio of lift to drag 0.4, which is the number that has been taken as a basic number, focus, or rather you could say ballpark figure of the beta, and you get 5.8, meaning if the depth is 1, the width is 5.8. And that's not good. I mean, that's not bad. It's a good number. Okay. I should tell you that Mother Nature likes to do wide channels. She likes to do wide channels. There are and what's a wide channel? By definition from the book by Chow, a wide channel is a channel where the width is 10 times greater than the depth. Let's take a look at here. This is interesting. And it just occurred to me. 10 times greater than the depth. So over here, by the time we get to 10, we're over here. 10 times, yeah, here it is, 10 times greater than the depth. Let's not go negative. Let's just go positive. Around here somewhere, between 8 and 11 for the positive number, right? So that means that in nature, the friction angles that prevail over in nature are going to be more like 15 degrees, according, if everything is okay here, the comparison, the analogy. Because there's going to be clay. There's always clay out there, silt and clay. The silt also brings the friction angle down. So there's going to be silt out there and perhaps a little bit of clay, and that's going to bring down the friction angle, and you're going to go wider to 10 to 15 and so forth. So that subscribes to the rationale that Chow said that, actually Chow didn't say it. Chow just said for a hydraulic, for a channel to be considered hydraulically wide, the width to depth has to be more than 10. And he's correct. But the question is, the next question is, are channels likely to be less than 10? And the answer is not likely, unless you put it together. If it's a channel built by nature, self-formed, it'll go 10, 15. There are some channels out there in flows, or rather in rivers that transfer a whole lot of sediment, where the width to depth ratios reach 50 and even 100. The width 100 and the depth 1. But it would not be a surprise to see 20s or around there somewhere. Okay, so that is kind of goes on to show you that that there is silt everywhere. Because if it were just sand, it would achieve what Lane said, 4 or 5. It would be in this range. But then it would have to be forced to be a friction angle on the size of 35. And you won't find that unless you have a channel which is 100% sand, clear sand, and those channels are there, but they are not very common. So that is the best that we could say about channel morphology at this time to explain and to use the Lane relation. So note that these, what I'm talking today, it's not bolded. That means it's not going to be on the exam. So you can take it lightly. From now on, it's 6:09 right now. In the next couple of 30 minutes or so, I'm going to talk about very complex subjects that we explored at the beginning of our tenure over at Colorado State. I spent 7 years at Colorado State, 3 as a student and then 4 as a professor. I was an assistant professor for 4 years at Colorado State and Fort Collins. And we did a lot of work, numerical analysis. We published a lot of papers, which allowed us to move to California. Because in order to get a position like mine, you had to have a record even before you aspire for the position. And we had the record. So we came over here and we, I guess, won the position of associate professor here at San Diego State in the year 1980. I became associate professor here. And before that, and right after that, I was working all kinds of stuff out there. This is one of the papers that we had written over there, where we published it in there's a mistake in here. There's a mistake, you can see. It says original version 1992. But if you go over here, the original version, it says 1982, 83. No, it's 82. It's not 92. That's a mistake. Well, you know, I told you earlier that there's mistakes. I get to change this and put original version 1982. And I say that because the celerity of transient bed profiles is a subject that had preoccupied me extensively throughout the late 70s. No, from the beginning, from 73. And how to study it, how to calculate it. And eventually we came up with 2 papers. One of them, which is extremely theoretical, that I'm not going to touch here today. I cover that paper in our course 632 class, Computational Hydraulics, that I taught last year in the fall semester. And obviously, I'm not going to get to teach that anymore because this is the end. This is my last semester. But the point is that we had that paper, but I'm not going to present that paper because this paper is strictly numerical analysis, and this course is not numerical analysis. But there's the other paper, which is what it was a technical note called Celerity of Transient Bed Profiles, which I feel assured that I can treat it over here and interest you in the subject of morphology, which is the objective. So this paper is called Celerity of Transient Bed Profiles. It's not a paper, it's a technical note. It's a short paper. For those of you that don't know, what's the difference between a paper and a technical note? The difference, at least it used to be, because I haven't been I'm ashamed to say that I haven't been publishing at ASCE for the last at least 15 years, if not more. But not ashamed, but I confess that that is the case. The rules were like this. Your paper, if you're going to do a paper, it could be up to 16 pages, printed pages. And if the subject is not meaty enough to justify a paper, to our judgment, they said, you can still publish it as a technical note. But the technical note is limited to 4 pages. So it's 25% length. And the substance, well, you know, it's not too meaty or substantive as the paper. So I guess we should say that this particular technical note that we're now looking at was like that. It was a technical note. What I wanted to show in here was that we had a formula to calculate the speed of the transients, the speed of the wave. And we wanted to verify it and see if indeed it was correct. It's interesting for many river engineers, if they have a transient, if you find a transient at the bottom of a river, to figure out what its celerity is. So this is a transient, and a transient is a wave. This is a sand wave. It is moving by rolling and sliding along the bed, and the movement could be expressed as a celerity. That means the velocity of the bed, the velocity of the bed. So the question is, what's the velocity? In feet per second or meters per second? Can that be calculated? And the answer is yes. Many attempts have been done through the years, and we did that in the late 70s. And like I say, I published another paper, of which briefly I took a chart and I put it in here. So let's get going in here. There's an urgent need for improved analytical tools with which to assess the propagation of bed perturbations. I should tell you at this point that I have a friend of mine, his name is Wally Walters, who retired from Battelle Northwest maybe 20 years ago. He was a classmate of mine. He retired early for whatever reason, but he wrote his master's degree for his master's thesis at San Diego State. He wrote a paper on the transients in the lower Mississippi. Apparently, the lower Mississippi has got transients because the Army Corps and many other people, scientists and so forth, are studying everything that happens in the lower Mississippi. It's a much studied river. So they discover these transients. And then the question is how big they are. And also the next question is how fast they move, because all these transients are on their way to the Gulf. So how long is it going to take for them to the Gulf? So Wally, my friend, my colleague, wrote a thesis on this subject. And he said, if I remember correctly, recently I asked him to send me his thesis, another copy, because I probably misplaced or lost the previous copy that he sent. I had a copy 25, 30 years ago. But things have happened, and and I can't find everything that I had owned in the past. And he's going to do it. But at the time, I remember what he said in his thesis. There was 1841, there were a couple of earthquakes in the Midwest along the Mississippi. One of them was over at New Madrid. New Madrid, as you know, is a town in Missouri, I believe. New Madrid, Missouri. Actually, it's on the border with Illinois, because the Mississippi River is the border between Missouri and Illinois. And New Madrid happened to be on the side of Missouri. New Madrid, Missouri had a big earthquake. Actually, had a series of earthquakes, because apparently there's a tectonic plate around there somewhere, or passing through. So if you're going to have a strong earthquake in the United States, it's probably going to be at either New Madrid or El Centro. El Centro is also well known for its strong earthquakes. We had a very strong earthquake, I believe it was in the year 2010, very strong earthquake in New Mexico, which was not Mexico, what did I say? El Centro. I'm confusing El Centro with New Mexico. El Centro, California. And I wasn't there, but I saw a lot of the stories about the earthquake. At any rate, New Madrid had a couple of earthquakes. I believe the first one was 1801, and the other one was 1841. And that earthquake caused a lot of damage, a lot of havoc, I guess is the word. And what happened was that at the time, there was not a whole lot of buildings out there. They were low anyway. But the point is that 1841, right? Cities were just getting formed at the time. But what happened was that the earthquake succeeded in tearing apart the bluffs. Let's explain that. Tearing apart the bluffs. Well, the bluffs are the scarps, the vertical slopes that the Mississippi River Valley has. Now, you have to go long. I don't recall exactly how much, but it's got to be in the miles, 10, 15, 20 miles. But eventually, you get to the bluffs. The bluff is vertical as opposed to horizontal. The Mississippi River has a valley, very smooth valley, right? All the sediment that settled there for years, millions of years actually. And then the bluff. So when the bluffs get torn, destroyed, because they're vertical anyway, they're unstable, that sediment that was kind of opened up would have a tendency to move into the river in the next flood, the next rain, the next strong rain would do that. And that's exactly what happened. So what happened, according to Wally, was that all that sediment that was in the bluffs came down and got into the river, but it was extra sediment. So the river doesn't have any power to hold to the extra sediment. So in accordance with Lane's relation, it would drop that sediment at the bottom. The river is very large and it could do that. Mississippi River, I don't have recent data, but I think the depth of the Mississippi River must be on the order of 20 meters, which is about 60 feet. 60 feet, average depth. Exactly where, I don't know. I'm just pulling up a number out of the air in here. Obviously, the 20 depth should be around, I would say around Carroll, which is kind of considered to be in the middle between Minnesota, St. Paul, Minnesota, Mississippi River, and New Orleans in Louisiana. Carroll, Illinois is in the middle. There's all kinds of stories about Carroll, Illinois, but I'm not going to get in there today. I think you heard me talk about that already. The flood of Carroll, Illinois, 2011, and I was there. Right at the flood, I was there. So anyway, so what we're doing in this paper is that we are taking our own formula and testing it with Sony's data. Who is Sony? Sony, I believe he was a gentleman working out of India, maybe a professor. We would have to look at the reference. Let me just check this. No, I don't have a click. I should, but I don't. Clickable, because I have most of my references clickable. But Sony out of India worked this in the lab, and he came up with the velocity profiles. He documented these velocity profiles. And I figured that I could use my formula and see if Sony's data matched my formula. And that's what we did in here. So it's really true morphology, celerity of sediment waves. That's very good. So for the theoretical background, we performed a linear stability analysis on the sediment equations, not the water equations. The S-curve, which you have heard me talk about, was on the water equations, simple water equations. This was more on the sediment equations. And we came up with this formula, where we very smartly non-dimensionalized the celerity, taking out the transport function. So the transport normalized dimensionless celerity is C sub naught or C sub star over phi, where phi is a transport function. And we came up with this formula, okay? And we defined the C star, which is the celerity over the velocity or the mean velocity of the flow. And we defined the sigma star, which is our sigma star. This is what gave us fame with the S-curve, because we were the first people to derive this parameterization of all the water equations to come up with a consistent, dimensionally homogeneous and dimensionless presentation of the whole process of wave propagation. So this is the number here, the important number. We call it the reference, the characteristic length of the perturbation, which is The L, the length of the perturbation, and the L sub O, parametrized or non-dimensionalized with an L sub O in the numerator, where the L sub O is an indication of the friction, because it's D sub O over S sub O. The friction would determine the D sub O, and the S sub O is there to determine the flow. So basically, this is a parameter, which is the characteristic length. And we were able to identify this equation after, like Marcus did, after several tries that led nowhere, trials that led nowhere, like Marcus in his equation. We finally figured this out by borrowing from the work of Leahy and Woodham, 1955, I'm sorry. They did a great paper on the kinematic waves, and they said, matter-of-factly, that this is an important equation or the important parameter, and then left it at there. They didn't pursue it. And I figured I was kind of desperate. I need a parameterizing formula, or rather value. And I used this, and it worked all. It fell into pieces, all of it, all of a sudden. So this is why I call Professor Ponce's luck, because I could have not found this number, and I would still be there trying to find it. But no, we did that. We did that in the fall of the year 1976, right after I had graduated from PhD school at Colorado State. We were so eager to get this thing with this work done, because we knew that there was out there gold at the end of the rainbow, that we proceeded right after I got my degree. I started work on this project, and it took about 3 months to do every night. Well, we did it. I had an error in experience. We also had a lot of experience at that time. So we finally came up with these equations, which are kind of similar, but not the same, because these equations have sediment. The S-curves don't have sediment. So we got these equations. You can see I'm not going to bore you with all these details, but we also came up, we could simplify it. For sufficiently large values of sigma star, we could simplify it for the transport normalized dimensionless celerity, which is this, C sub star phi, to be only a function of the Froude number. Which is interesting, because if the Froude number gets to be critical, 1, then the celerity is infinity, which is true. Anytime you have a Froude number equal 1, you can't see the bed. It disappeared, right? You cannot see the bed. The bed's transients, because it all became obliterated by the flow itself. So here we go. It's a fundamental equation. It works for the conditions of Froude less than 1, much less than 1. Okay, because by the time it gets to less than 1, it goes to heaven here, right? Can you see you climbing it? It goes to infinity. But the more likely values are 0.1, 0.2, 0.4, 0.5. Rivers, normal rivers usually don't go above 0.5. They only go 0.5 when they're in torrent mode, and they get to 0.6 or 0.7, 0.8 maybe, okay? And we should also tell at this point the formula or the concept that was developed by, God, I forgot his name again. The gentleman that said that natural rivers don't get the Froude number above 1. They don't even get to 1, he said, because it's impossible. Mother Nature doesn't like, the statement is that Mother Nature doesn't like natural rivers with Froude numbers greater than 1. That's what he said. And I truly ascribe to his statement. I believe in his statement, because we have studied this extensively. And by the way, this is also part of the exam. So pay attention to what I just said. Okay, so experimental verification. The experimental verification. So we were supposed to take our equation, figure out what the wavelength was, and then compare it with data, compare it with the data of Sony. And we did that. We came up with the sigma star equal to 12, based on the D sub O, L sub O, no, L and S sub O, the data from Sony. And we came up with the celerity was 0.0021. And then we measured the 10 measurements of Sony, and it came up 0.00229. We can't fudge these numbers. It came up like 70%. And I thought it was great, because I know sediment has a hard way, we have a hard way to pin down sediment exactly. I was extremely happy that we got in the ballpark. However, the agreement could be a little better if we consider that this number of 0.0021 is for small perturbations. Small perturbations meaning less than 5%. But in here we had a 20, 30%. So we had a correction coefficient that had been developed by Lopez Garcia, who was one of our students at the time, or earlier, 1977, 78. And he said, well, if you have large perturbations, then you can apply a correction coefficient, and he gave us the correction coefficient. So long story made short, our 0.0021 converts through the correction of Lopez Garcia to 0.0025, which is within 10%, 15% of the actual measurement. The actual measurement, we cannot disagree. Actually, you can disagree a little bit, but not too much. We can take the wave in the different place and so forth. But in point of fact, now we at this point consider that we were correct. Interesting thing about this is that when Wally Walters did his calculation, I remember this long time ago, maybe 30, 35 years, because he got a degree back in the year 1978. So I asked him at the time to give me his parameters, his hydraulic parameters, the wavelengths, the depths, the friction, the channel slope, and so forth of the Mississippi on the reach that they were looking at it. And I plugged in the calculations into our model, and then figured out a celerity, which is on the order of this celerity, by the way. It's not uncommon to get 0, 0, 2. So that means 2 centimeters per second. That's not uncommon for the typical fruit numbers, 0.2, 0.3. Remember, it varies with the fruit number. And we were able to calculate that those bluff breakages of the year presumably from the year 1841 in New Madrid, Missouri, had taken all this time from 1841 to 1978 when we did this calculation, 78, 79, to get to the Gulf at the speed that they were going, 2 centimeters per second. You can do that calculation. All you need to do is go out there, figure out what the parameters are, hydraulic parameters, and then figure out what the distance is between Cairo and New Orleans, and figure out at that speed, how long would it take? And it normally would take 150 years, or 120, 130 years, which is interesting. This issue of the celerity of transient bed profiles had preoccupied us since the beginning of my career at Colorado State. Because what happened was that the link canals, which I believe we have covered that either here or in the other class, were not managed 100% correctly in Pakistan, and a big transient had dropped into one of the channels. I believe it was it was not the TP or the QB. It had to be the Chas-Magellan, I believe. The Chas-Magellan link canal had dropped. They had dropped by either surprise operation of the gates. They had dropped a big transient. So it was one of our issues out there to figure out how long was it going to take that transient to move. And it was 70 miles a channel. We figured out, I don't recall at this point, but it was a few years before that transient would get to the other side. That means to the other outtake and intake for the next channel, because we know that the links are all connected. That's why they are called link canals. Okay, so with that, I'm done with this, and I'm going to go to the last one, modeling alluvial channel bed transients. I know that this course has been tough for you guys because it's been difficult math, difficult mechanics. So I'm going to try to be brief in here. I'm not going to quiz you on what I'm going to say here today, but it is important because it is into the future. If you're going to get into sedimentation engineering, you eventually are going to do transient modeling, because steady modeling and it's not enough. People are going to require that you transient modeling. It's fancy. We can do it now. There are models to do that. Typically, it would be a subject that people would do for a master's degree, to do a transient modeling. Although I must tell you at this point that I'm not sure at this point if that is appropriate. It used to be appropriate 40 years ago, but not anymore. Maybe things have changed a little bit. But at any rate, it's a good subject. It's a very technically challenging subject. So how you model alluvial channel bed transients. We did that at the beginning of our career, 1977, 78. This paper is published 1979. The date is correct. If you look at this chart in here, it says sandbed profiles at intervals of 96 days. So 96, 192, and so on, 192, and so on and so forth. What is this? This is the sand wave. This is the sand wave. So the sediment is being trapped. The sediment is being trapped at the dam. First, it drops over here immediately right at the headwater, and then it starts moving downstream until it gets to the dam over here. So this sediment is being trapped at the dam. It's a positive sand wave in here. Of course, you think this is going to be a wave because it's like a wall of water. No, no, no. We're talking here about distorted scales. This one is miles, 4 miles, and this one is 6 feet. No, not even 6 feet, 4 feet. So 4 feet in the vertical and 4 miles, which is 4 miles is 5,200 feet, so 20,000 feet. So the scale is totally distorted, which is basically the only thing we could do. That's the only way we could plot it. Otherwise, you can't see it. So we did this calculation. We have the governing equations, which are the equations of motion, and the so-called Actionary equation. In order to do this, we have to drop this part over here because it's too complex to handle. And we, at the time and even now, do not believe that it really mattered. So we dropped this equation, and the resulting two-term equation is called, in the jargon of sedimentation engineering, it's called the Actionary equation, E-X-N-E-R. Very popular equation, which is part of HEC-RAS. You know, HEC-RAS, you of course have practiced or heard, or we used HEC-RAS. Many people have used HEC-RAS. A lot of people use it. It's standard practice working with HEC-RAS. And HEC-RAS has steady, unsteady, sediment, 2D, and water quality. Now they have a fifth stage of development. They've been doing this since 1998. So there's 24 years of development of the GUI version of what used to be HEC2. It used to be called HEC2. I don't like to call it HEC because it sounds HEC. HEC2 was the old version, which the character cell version. And in 1998, they put it together as GUI, and then they started developing the GUI little by little, and every 3 or 4 years, they would come up with a better version, a newer version. So by now we have, again, steady, unsteady, sediment, 2D, and water quality. And I do believe, if I'm correct, that they're working on the 3D. As to when they will release that, I don't know. One has to check every once in a while the new versions and see if they are about to release the 3D. And the reason I'm saying that they're going to do that is because they're behind the Europeans. I believe the French and the Spanish, and I don't know about the Germans, maybe, they have already worked on 3D workable operational models of 3D flow. And the question is, once you have 3D flow water, can you go to 3D sediment? And that's the next step. Very complex subject. I certainly wouldn't get into that anymore. I guess you could say too old to get into that. That's good job for people that are in their late 20s and early 30s. Okay, so that we did the calculation, and we used to find a difference, which we're very good at. We used the Breison scheme, which is this over here. Those of you that took computational hydraulics already heard me talk about the Breison scheme, very well known. Due to Breison, it was a French engineer who developed the scheme at the time, 1961, and he became very famous because it was a very workable scheme. And it was based on this magic number, which we call theta, which is a weighting factor. And I'm not getting there. I'm not getting there right now because I get in there and I can't get out in an hour. But the point is that without that theta, the system wouldn't work. It was the theta that made it workable. It is a numerical diffusion coefficient that makes possible for the errors that always pop in numerical analysis to be obliterated by some kind of aspirin. I have described it as aspirin because it kind of obliterates all the inconsistencies and headaches of the modeling itself. It's a good term, aspirin. You heard me talk about that, those of you that took computational hydraulics. So then the boundary conditions, stability and convergence, we had to talk about that because that was our subject in those times, stability and convergence. Because a lot of people studied stability, but they didn't get to the convergence. We studied both. Numerical experiments. Now we're going to go into the formation of sand waves, the migration of sand waves, erosional and depositional transients, and so on and so forth. I already shown you the sediment trapping dam modeling. So this can be done. We did it. But we did it on a demonstration basis. From here on, if you wanted to do it for an engineering practice or problem, then you got to be paid by somebody. And this is exactly what happens. People go work for the companies and the companies get paid to do this work. I remember when one of the professors out there who used to work, or professor doesn't work there anymore, but she used to be with West Consultants, and she was doing RAS in and out. And one day I told her, I asked her, I said, because I don't do that in and out. I may do that once every 3 years, but she was doing it every week or every month. So I asked her, I said, by the way, I'm curious to know how much you guys charge to do a HEC-RAS run or a study. And she said to me, at that time, that's 2005, so almost 20 years ago, she said to me, we wouldn't touch it for less than 20,000. And then I talked to Parra later on, 10 years later, Professor Parra, that has his own company in town. And Parra said, we wouldn't touch it for less than 40,000. What are the 40,000 for? Is to pay the engineers that are going to spend typically a month doing this work, running it, making sure it works, and so on and so forth. So that's the story. Degradation below dam, that's the problem of laying. So one is 96 days, the whole thing. So the model can do all this stuff. It can do the filling of a dam upstream, less lane would have predicted, or the degradation below the dam, or the removal of a sand bed profile. If you make a hole in there, it will move downstream and it would endanger a bridge. If you have a bridge over here, it would endanger it. And a story that I have in here, I have a couple of minutes, is that when I presented this in the year 1977. In the year 1977 was the first time I presented this, and my boss at the time, Daryl Simons, used to be there at the meeting for some reason, or I think it was a thesis or something. I don't remember the details, but he said that the stuff would move downstream, and he corrected me. He said, Ponce, I do not believe what you're saying is correct, because our experience tells us that the stuff would move upstream. In other words, that this is wrong. Is to move upstream, and you're calculating it to move downstream, right? One day, one interval, two intervals is moving downstream. So then at that time, of course, I didn't have the wherewithal or the force of mind or energy, whatever, to argue with my professor. That's not a good thing to do, certainly not in public. So I said, oh, okay, fine. And I kept quiet. Survive is the issue here. And then later on, I got to thinking about this. And I said, it is not possible that I could be wrong. Because if I'm wrong, then the basic state equations, continuity, momentum, are wrong too. They're telling me that it's supposed to go that way. So there must be something else in here. I'm not going to discuss, I'm not going to say that Professor Simons was wrong. I'm just going to say that we're not talking about the same thing. He's talking about a process that moves upstream, and I'm talking about a process that moves downstream. And eventually, I don't know exactly when it was, but over the years, I looked at this many times and I realized what the problem was. The problem was that I was looking at one-dimensional flow, and I was using the one-dimensional equation. He was using a process that it's called head cutting, which is essentially three-dimensional. In other words, there's going to be, because of this drop in here, there's always going to be head cutting in here because of the cataract, the fall that will form in here. So there's always going to be a head cutting, but the head cutting will find its own equilibrium and it will stay there a long time. We don't know. I cannot model head cutting because that is three-dimensional and I don't have a three-dimensional model, but I can model one-dimensional downstream. So now we believe that we were correct and that he was also correct, but we were looking at apples and oranges, different thing. But I did survive because I didn't argue with the professor at the time. Daryl Simons passed away the year 2005, I believe. He was very old, about reaching 90 at that point. But this was only in 1977. He was only about 70 at the time. So the sensitivity, and finally we get to the sand waves. These are the sand waves. And we were looking at the weighting factor. Remember I told you that, that the weighting factor theta was instrumental in making the job work itself out and work. And here we show that that's exactly the case. It's the way it's going to happen. First of all, we identify the Courant number, which is something I'm not going to talk about because it's too much already. The spatial resolution is the resolution of the numerical model. It has to be high. It has to be 40, 60, 100. You're going to have a resolution of 3 or 5. because then the data gets into the grid size and it doesn't move, right? So it has to move, it has to be 40. Here we have 40, 40 is a standard over here. And we use the theta, with theta here we use 0.6, 0.8, and 1. And note that the 1 came out really nice, and the 0.6 was sharp. So then the question in here is the flow actually going to be sharp or like that, or smooth? And the answer is we don't really know. It'll depend. I can't tell you, I have not gotten in depth on this, but I'm just showing the way it would work. So if you wanted the model to run, you got to run it with a theta equal 1, which would provide in there enough diffusion of a numerical nature so that you can run the model. Otherwise, the model is going to get to be vertical, and once the model gets close to vertical, it will drop totally on you, because the model is a linear model and cannot take changes, abrupt changes within one time step or space step. Everybody knows that at that point we will lose the model. So that's the story of this. So recommendations of stability, and so on and so forth. In summary, we develop a mathematical model to simulate bed transient and propagation. This technique allows the implicit numerical modeling of bed transients. Instability due to ill posing of the sediment transport, that's something we discovered at the time. We didn't spend a whole lot of time explaining that. We analyzed stability and convergence, which was our subject at the time. I wrote several papers just on the issue of stability and convergence. Why? Because at the time, most people that did this work will concentrate on stability, but they didn't get to convergence. But we had a methodology that allowed us to do both at the same time. So we wrote a bunch of papers on stability and convergence. Criteria established to ensure a successful model. Convergence is shown to be primarily a function of the temporal resolution, or spatial, the same, and the tie between the two is the so-called Courant number, and the weighting factor, which plays a secondary but nonetheless important role. The weighting factor was actually pot of gold at the end of the rainbow. We worked for 20 years on this subject and came up with at least 15 to 20 papers on the issue of numerical diffusion and how does it affect physical diffusion and when you should use it and when you should not use it. That led to my work on kinematic waves, diffusion waves, and dynamic waves. So I'm going to stop there. Let me stop the sharing here, and I'm back. I'm back on the screen. Thank you very much.